Hi everyone. So in this video we are going to solve this particular problem which was asked in GATE 2018 examination. Okay, a very good question it is, and a lot of people have given different solutions. So here I will try to give my solution, what should be a particular approach. Okay, but before starting the solution you should watch one more concept, that is sequence generation. So I will add up the video of sequence generation right now only. So first we will see that particular concept of sequence generation, then only we will start the solution, because this concept is not usually taught at a lot of places. Like people generally do not teach this concept. So once watch that concept, understand what do you mean by sequence generation, how do you design a circuit of sequence generator. Once you are done with that, then come to this question. After that it will be a cakewalk for you. Okay, then you will realize that this question is based on sequence generation, not on FSM. Okay, so I will add up the video, watch that video, and then come back to this particular solution. Okay then, so let's see sequence generation now. Hi everyone, so now we are going to study about our next topic, that is sequence generation and detection. So first we will study about sequence generation. We will generate a particular sequence and then we will see how to generate a particular sequence. So sequence generation is a very simple topic, but sequence detection is a bit typical and also it is very important as well. And we will see the complete depth, and once you watch this particular video, after that there will be no confusion in sequence generation as well as in detection. First let's start with sequence generation. So what you need to do, you need to design a circuit. You need to design a circuit such that it generates this particular sequence, which is 1 1 1 0, then again 1 1 1 0, then again 1 1 1 0. So this sequence you need to generate. So what does that mean? That if first clock pulse come, if the first clock cycle is coming, then 1 should come. Then another clock cycle is coming, then another 1 should come. Then another clock cycle is coming, another 1 should come. Then another clock cycle is coming, 0 should come. Then another clock cycle is coming, 1 should come. Clock cycle 1, clock cycle 1, clock cycle 0. So in that manner it should go. So this one and this one, these are different. This one and this one, these are different. This one and this one, these are different. Certainly 0 is different from 1. That's for sure. Are you getting my point? With every clock cycle, 1, then again 1, then again clock cycle, again 1, then again clock cycle, then 0. So these ones are different. These should be denoted differently. So if I say, let's just say 1 is already different than 0. So if I say that if I introduce another bit, that is 0, and then I introduce another bit 1 in front of this. So now this one and this one are different, right? It is 1 1 and it is 0 1. But how will I differentiate this one? Either I will have to connect a bit 0 or I will have to connect a bit 1. So if I connect a bit 0 here, then these two are same. So that's an issue for me. And if I connect bit 1, then these two are same. So that's an issue for me. So using only one bit I cannot do it. But if I use 2 bits, then what I can do? If I use 2 bits, I can give 0 0 to this one, 0 1 to this one, 1 0 to this one, and 0 0 to this one. Now all 0 0 to this one, I can give anything. 0 0 I can give here, 1 1 I can give here, 1 0 I can give here. Here also I can give anything. I can give 0 1 to this one, 1 0 to this one, 1 1 to this one, or anything else. Basically I need to differentiate all these 4 bits. So 1 1 1 0. Now all these are different. All 4 different. Now what has your question become? Now your question has become that you need to generate a sequential circuit which will go from 0 0 0 1 to 0 1 1, then to 1 0 1, and then to 0 0 0, and then again back to 0 0 1. And here at the last bit, I will collect my output. So at the last bit I will collect my output. We will see the design, it will be more clear to you. So what did I do? I needed to generate this sequence 1 1 1 0. Then I got to know that my 1 is being repeated 3 times. So to differentiate that I would need another 2 bits, 0 0 0 1 1 0, and for 0 I can connect anything. So this is the state diagram I am getting. Here there are 3 bits, that means I would require 3 flip-flops. 3 flip-flops required. So using D flip-flop I can design it. This counter I am going to design. This particular counter I will design, and across this bit, if I call this as Q2, this as Q1 and this as Q0. So across Q0 I will collect my final output. So first I will see 1 1 1 0, then again 1 1 1 0. Are you getting this point? We will design it. Let's see. So now what has your question become? You need to design a counter which follows this sequence from 0 0 1 to 0 1 0 1 0 1 to 0 0 0. So this is how I am gonna design. I am designing a synchronous counter. This is my synchronous counter. So I told you I have given the complete method how to design a synchronous counter, and we have seen a lot of examples as well. How do we design a synchronous counter? First we write down all the possible combination. So from 0 to I am going to 0 0 1. From 0 0 1 to I am going to 0 1 1. Then from 0 1 1 to I am going to 1 0 1. And from 1 0 1 to I am going to 0 0 0. And rest all these are don't care. So these conditions will not even occur. So these conditions are don't care. And what is D2? D2 is simply Q2 plus. What is D1? D1 is simply Q1 plus. And what is D0? D0 is simply Q0 plus. So these are don't cares. Right? Now my D2 will be function of Q2, Q1 and Q0. Same goes for D1. That will also be a function of Q2, Q1 and Q0. And same goes for D0. That will also be a function of Q2, Q1 and Q0. And if we write down the minterms, what are the minterms for D2? Minterms for D2 are 0, 1, 2, 3 plus don't care 0, 1, 2, 3, 4, 5, 6, 7. So don't care are 2, 4, 6, 7. What about D1? D1 has a minterm of 1 and don't cares are 2, 4, 6, 7. What about D0? D0 has a minterm of 0, 1, 0, 1, 2, 3 and minterms are 2, 4, 6, 7. Right? So I can make the K-map now. This is how I will make the K-map. Okay, and from there I can get the value of D1, D2, D1 and D0. So what is the value of D2? So here I can see a quad. So this process we have already studied, that's why we are moving a bit fast here. So this is a quad. What is constant here? Only Q1. Again saying I am having elaichi so that I do not cough. I am not a fan of Ajay Devgan. Okay. Again and again I am repeating it so that no one comments, sir, are you a fan of Ajay Devgan because pan masala? No pan masala. I don't eat these kind of things. Just I am having the elaichi. If you have the elaichi in your mouth, you will never cough will never come. So that I can explain the things better, right? So what about D0? D0 is Q2 bar only, right? D0 is Q2 bar. So this is your D2, D1 and D0. So D2, D1 and D0. Okay. Now the thing is, you will design this particular circuit. This is the circuit, and here you will collect your output. This is your final output. Because what we wanted this sequence 1 1 1 0, and this is what you are going to get 1 1 1 0. But the thing is, you need to check whether it is going from lockout problem or not. Whenever we design a synchronous counter, we see what will happen to these states, whether it is going into lockout or not. So if it is going into lockout, then that will be a problem for us, because here we have assumed that it will be starting from 0 0 0 0. But what if it starts from 0 1 0? Where it will go? So since I am done designing this, now I will see whether I am suffering from lockout problem or not. So what will be my Q2 plus? Q2 plus will be equals to D2, and D2 is equals to Q1. What will be my Q1 plus? Q1 plus will be equals to D1, and D1 is equals to Q2 bar, Q1 bar into Q0. And what about Q0 plus? That will be equals to D0, and that is equals to Q2 bar. So Q2 plus is equals to Q1. So 1 0 1 1. Q1 plus is equals to Q2 bar, Q1 bar into Q0. So this is 0, this is also 0, this is also 0, and this is also 0. all these are 0, and Q0 plus is Q2 bar. So 1 0 0 0. So let's write it as 2. So from 2 to you are going to 5. What was the cycle here? What was the cycle? I designed for 1 3 5 0. So what I designed? 1 3 5 0, 1 to 3, 3 to 5, and 5 to 0, and then came back to 1. This is what I designed. Now let's check. From 2 to 5 you are going. So 2 to 5 you are going. No issue here. 4 to 0 you are going. No issue here as well. 4 to 0 you are going. Here 6 to 4 you are going. 6 to 4. 6 to 4 you are going. Again no issue. 6 to 4, then 4 to 0, again no issue. Then 7 to 4 you are going. 7 to 4 you are going. So 7 to 4 you will go, 4 to 0 you will go. So there is no another loop. There is only one loop. So there is no lockout. So the design is perfect. Design is perfect. So even if in the worst case, if it starts from 6, then after one clock cycle it will go to 4. Basically, if it starts from 1 1 0, so first you will receive 0 output, then you will receive again 0 output. After that you will receive again 0 output, and after that you will have the corrected output. That means 0 0 1, 0 1 1, and 1 0 0. This is what you are expecting. Then again 0 0 0, then 0 1 1. What we wanted? 1 1 1 0, right? We wanted 1 1 1 0. So that you will be getting 1 1 1 0. So 5 is 0 1 0 1 actually. 5 is 1 0 1, and then 0 0 0. So the 1 1 1 0 you will be getting. You will be working in this loop only. You will keep on working in this loop. Even if you are starting from 6, 7, 4 or 2, eventually you are going to fall in this loop only. And if you collect your output here, you will receive 1 1 1 0, again 1 1 1 0, and in that manner it will keep on going. Okay. So this is what this is how we can design it. So this was our first way of designing. But here what is the issue? You can already see, if you are designing a synchronous counter, there is very high chance that lockout problem may occur. So once your designing part is done, then after that you check that if there is a lockout problem or not. And when you find there is a lockout problem, you redesign it. So that is an issue for us. So that's also a good design. That's also one of the option. But there are other methods as well. So let's see method 2. So in method 2, I will be using asynchronous counter. So what I will be doing? So here you are not going to understand anything. Okay. So what I need to design? 1 1 0. This I need to design. Okay. Now let's just say I have a up counter of 2 bits. So let's just say it's starting from 0 0. So then it will go to 0 1, then it will go to 1 0, and then it will go to 1 1. Now what I can do? This is the up counter. There will be 2-bit output, 0 0 0 1 1 0 1 1. So whenever you get 0 0 output, I will design a combination circuit here. I will design a combination circuit, and this will be my final output. So whenever I get 0 0 here, this should give me 1. Whenever I get 0 1 here, this should give me 1. Whenever I get 1 0 here, this should give me 1. And whenever I get 1 1 here, this should give me 0. Then again 0 0 would come, 1 1 1 0. So here what I will be having? 1 1 1 0. Again 1 1 1 0. Again 1 1 1 0. Is that a good idea? If you did not understand it, you will understand it certainly. Okay. No need to worry about that. So let's see the example. So same example we are taking. Design a pulse train generator. So what I am going to do? I will design a up counter which gives me the following output. So this I am calling as Q1 and Q0. So my up counter will give me 0 0 0 1 1 0 1 1. Now at the output of up counter, I will be using another another combination circuit, which will give me for 0 0 it will give me 1, for 0 1 it will give me 1, for 1 0 it will give me 1, and for 1 1 it will give me 0. So this I will be using. Okay. So then with respect to these outputs, I will design a combination circuit which give me outputs respectively 1 1 1 0. So what will be my F? My F is simply Q1 bar plus Q0 bar, or you can say Q1 Q0 bar. F is Q, you can write the max terms, which is Q1 bar plus Q naught bar. So Q1 Q naught bar. So simple, what is this? This is your up counter. And here I am collecting my final output. Final output. So what will happen? First 0 0 will come, output will be 1. Then 0 1 will come, output will be 1. Then 1 0 will come. Here it is Q1 into Q naught bar. Q1 into Q naught bar. Then 1 0 will come, output will be 1. And then 1 1 will come, output will be 0. Then again the cycle will keep on going. Again 0 0 will come, output will be 1. Again 0 1 will come, output will be 1. Again 1 0 will come, output will be 1. Again 1 1 will come, output will be 0. So this cycle will keep on going, and at the receiver you will have 1 1 1 0, 1 1 1 0, 1 1 1 0, 1 1 1 0 in that manner only. Are you getting this point or not? So that's the way it will go. So this is also a good idea. But here we were lucky, we did not have to use any clear or preset input. But what if this example is given? Try it on your own, you will understand what is the catch here. You need to generate this sequence 1 1 0 1 1. This sequence you need to generate. First tell me how many flip-flops will be required. Look, here there is no concept that you need to differentiate these stages, that I need to differentiate this guy and this guy. There is no concept like that. Why is that so? Because each states are different. Each states are different. With respect to one stage, I am getting one output. With respect to other stage, I am getting another output. Basically, what do I mean is that if I design an up counter, which is 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. So with respect to this I will be getting 1. With respect to this I will get 1, then I will get 0, then I will get 1, then I will get another 1. So this is what I need. If this stage comes, what I am going to do? I am going to clear it. Say yes or no. Here I will clear it. This I don't want. So I want my output to go from 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0. Just as I get 1 0 1, output should be cleared. Are you getting this point? So number of bits in the sequence are 5. That means at least 5 you need, at least 5 combination you need where you can assign the output. At least 5 combination I need. The number of bits in the sequence are 5. If the number of bits were 4, here number of bits were 4. So I thought that at only 4 sequence I need. And if I need only 4 combination I need, and to each combination I can assign a value. So using only 4 combination I can assign these values. But now I have number of bits equals to 5, which are 1 1 0 1 1. So I need at least 5 combination to whom I can assign the value. At least I need 5 combination. So for using 5 combination, for getting 5 combination, how many bits do you require? 3 bits. And 3 bits means 3 flip-flop. Did you understand this point or not? I am designing it using asynchronous up counter. Okay. Number of bits in the sequence are 5. So what do I know? That each bit I will be assigning to a particular combination. I will be assigning 1 to a particular combination, then again 1 to another particular combination, then again 0 to another particular combination, then again 1 to another particular combination, and then again 1 to another particular combination. So I need at least 5 combination. And if I need at least 5 combination, then from 2 bits I can get only 4 combination. But from 3 bits I can get 5 combination. Usually there are a lot of formulas which are taught in this particular method, but we are not covering any formula here. We will not see any formula. We will think, okay, you are designing it using asynchronous counter. That means you are either designing up counter or down counter. Then you will use a clear input. Also, you know one thing, that is that if I am designing it using up counter or down counter, that means each combination is getting a particular output. 0 0 0 1, 0 1 1 1, 0 1 0 0, 0 1 1 1, 1 0 0 1. That means I need at least 5 combination. If I need 5 combination, that means required flip-flops are 3. Okay, well and good. I hope this is clear to you. So what I am going to write, Q2, Q1 and Q naught. With respect to that, I will have my output F. So these combination I can write. Okay. So if 0 0 comes 1, 0 0 1 comes 1, 1 0 0 1 0 comes 0, 0 1 1 comes 1, 1 0 0 comes 1. After that, what should be your F? F I am saying. There is a up counter. Okay. 0 0 is coming, F should be 1. Basically, this is the scene. That there are 3 output bits. This is your combination circuit. This is your up counter. So 0 0 is coming, 0 0 0 is coming, output should be 1. 0 1 0 is coming, output should be 1. 0 1 0 is coming, output should be 0. 0 1 1 is coming, output should be 1. 1 0 0 is coming, output should be 1. But in this up counter, I will use a clear input, which will make sure that these conditions do not even occur. Say yes or no. This clear input will make sure that these conditions do not even occur. Why is that so? Because let's just say if 101 is occurring, this 101 is occurring. So after one clock cycle, 101 will occur. And I do not even want this. I do not even want 101 to occur. Because I want this sequence to be repeated. 11011, then again I want to go back here. Say yes or no. Right? So this is the sequence I want. So I make sure that these conditions do not even occur. So all these will be don't care. What will be my clear input? Here I am going to break it, right? This, here I am going to break it. So this condition I do not want. What I don't want? Q2, Q1 and Q naught. 1, 0, 1. So there I told you a trick, and I also told you when that particular trick will be applicable. When it will be applicable, you are designing an up counter. Okay. Where you are starting from? If you are designing up counter, that means you are supposed to start right from the 0. Are you starting from 0? Yes, I am starting from 0. That means trick is applicable. Now, if you are designing up counter, up means you are high in your life. If you are high in your life, that means you will only look at 1. So if I am only looking at 1, so I need to design clear input. So what I will write? Q2 into Q naught. And Q2 into Q naught, 1 into 1. I want my clear input to be high. So 1 into 1 is 1 only. So my clear input is high. So this is the ideal design of clear input. What is the ideal design of clear input? This is the ideal design of clear input, which is Q2 into Q naught. Say yes or no. Right? So this is my clear input. I hope you already know this thing, because we have already studied this in a very in-depth manner. We spent around 2.5 hours just to understand this particular concept. When this trick is applicable, when this trick is not applicable, that we have seen in very in-depth manner, right? What about F input? Do you need to make a K-map here? What do you think? What about F? Do you need to make a K-map? No. What do I do is that all these don't squares are there. I can consider all these as 1. If I consider all these as 1, then I will be left with only one max term. That is 0, 1, 0. So I can write my F is Q2 plus Q1 bar plus Q naught. There you. Q2 plus Q1 bar plus Q naught. This is your final output F. Okay. So this I will be removing. So you should have a good aptitude that 1 1 0 1 1 is there. These are don't care. I can assume any value. If I assume one value here, I will be left with only one max term. So that will be Q2 plus Q1 bar plus Q naught. So that will be my F, and this will be my clear input. So this is how I will be designing it. You can see this is the clear input. What is the clear input? Q naught into Q2. So Q naught into Q2 is fed as the clear. So how do we design it? That also you know by the trick, and trick is applicable if you are starting right from the 0. And if you are designing up counter, that means you will be focusing on 1 only. So if I focus on 1, Q2 into Q naught is giving me 1. So that's it. So this is my clear input. Okay. This is my clear input. And what about this final F? This will be my output, final output F. So my final output is Q naught plus Q1 bar. From here Q1 bar would be coming, and from here Q2 is coming. So here I will receive my final output. So if first clock cycle comes, here you will have 0 0 0. So what you are going to have? 1. Then you will have 0 0 0 1, again 1. Then you will have 0 1 0, then you 0, then again 1, then again 1, then again this cycle will come here. So this is how you can design. Okay, so this was the method 2. The third method is using shift register. So that we have already seen with the help of an example when we were studying shift register. Okay, you can see the example. So this much knowledge is more than enough for gate aspirants. They can give this particular circuit and ask you the output, that which sequence it will generate. For gate aspirant, they will give this particular circuit and they will ask you what will be the sequence generated. So you can directly see that, okay sir, this is a down counter. Actually it is a down counter, but I need to make it up counter, so I will use this. Also I can use this here as well. Okay, so now it is up counter. In the previous design, did I make it up counter or down counter? Okay, it was up counter only. So here also we are using up counter only, so I should make it up counter. So this is a up counter. You will get to know that it will start from 0 0 0, it will keep on going. Then you will see where it is being cleared. Okay, it is cleared at 1 0 1. So if it is being cleared at 1 0 1, that means it is being cleared at 1 0 1. Yeah, right. It is being cleared at 1 0 1. So that means that will not occur. So it will count from 0 to 4 only. If it is counting from 0 to 4, so what will be your output? 1 1 0 1 1. Then it will keep on going. So if you can design, then certainly you can analyze that well. Right? You can certainly analyze this particular circuit. Right? So that's it about our sequence generation. Very easy topic, very straightforward topic. Let's see some common gate question which has been asked. So the minimum number of JK flip-flops required to construct a synchronous counter with the count sequence 0 0 1 1 2 2 3 3 and then 0 0. So 0 0. So in that manner they ask 0 0 1 1 2 2 3 3. So how would you show 0 at 0 only? How would you show 1 at 1 only? How would you show 2 in binary? That would be 1 0 1 0, and this would be 1 1, this would be 1 1. Now you need to differentiate this 0 and this 0, this 1 and this 1. Look, 0 and 1 are already different. You do not need to differentiate it, but both 0 0 are same. You need to differentiate it, and we are using synchronous counter. So we are using first design. So this is the design we are using. This design we are using. In synchronous counter, we need to differentiate everything, right? We need to differentiate all, and then we design a counter, and with respect to that we get our output. So if we are using synchronous counter, then we need to differentiate everything. Okay, so 0 and 0 both should be differentiated from each other. How I can differentiate it? Using 1 bit only, 0 and 1. Can I differentiate these two as well? Yes, using 1 bit only, 0 and 1. Then these two also should be differentiated, 0 and 1. These two also should be differentiated, 0 and 1. But here you are using 3 bits, so here also you need to use 3 bits only, no? Are you getting this point? If I am using 3 bits here, so here also I will use 3 bits. So what I should do is that first I should denote 0 0 and 1 in 2 bits. Then I need to differentiate. So this I will put 0 1, this I will put 0 1. Basically here 1 is repeated twice, 0 is repeated twice, 2 is repeated twice, and 3 is repeated twice. So differentiate 2 times. What I can do? I can add a bit 0, I can add a bit 1. So both are different now. So using only 3 bits, how many bits are required? 3 bits required. That means 3 flip-flops are required. That's it. Okay. Solve the next question on your own. 0 1 0 2 3. 0 1 0 2 0 3. So for 3 you would require 2 bits, that I know. So certainly I will denote all the numbers in 2 bits only. So this and this are already different. This is also already different. This is already different. What is the scene? Scene here is this 0 0. So these I need to differentiate. These I need to differentiate 0 0 0 0 and 0 0. Can I differentiate it using 1 bit only? If I connect a 0 here, this would be 1, and again I need to connect either 0 or 1. If I connect 0, this would be same, and if I connect 1, then this would be same. So using 1 bit only I cannot do it. So I need to use 2 bits. So if I use 2 bits, that means this will be 0 0, this will be 0 1, and this would be given 1 0. You can give anything to these. 0 0 you can give, 0 0 here also you can give, 0 0 also here you can give. So how many bits you need to use? 4 bits. And what does that represent? 4 flip-flop. So what is the answer? 4 flip-flop. If the question was in this manner, okay, try answering on your own. How many flops you will be requiring? What do you think? So it is 0. For 3 you would require 2 bits, so 0 0, then 0 1, 0 1, 0 1, 0 1, 1 0, 1 0, and that is 3 1 1. So you need to differentiate between these two and these 4. So what do you think what you will do? You need to differentiate 4. If you need to differentiate 4, then at least you require 2 bits, 0 0, 0 1, 1 0, 1 1. So all 4 are differentiated. Anything you can give here. Now what about this? If I give 0 0 here, at least I need to give 0 1. Apart from 0 0, I can give anything. And here also I can give 0 0. So how many flops you require? 4. Directly you can see that it is coming for 4 times. If it is coming for 4 times, then at least I would be requiring 2 bits to differentiate these 4. It is coming 2 times. Then at least I would require 1 bit. But here I would require 2 bits. So 2 bits for this and 2 bits to represent 3. So 2 plus 2, 4 bits you require. So answer will be 4 flip-flop. I hope you are understanding it. To represent the numbers, I need 2 bits. Because if I am getting state 3, then at least 2 flip-flops has to be there. From only 1 flip-flop you can get 0 and 1 only. So if I need state 3, then at least 2 flip-flops has to be there. So if 2 flip-flops are there, okay, it is fine. Now you need to differentiate 1 1 1 1. So 2 bits, 2 bits, 2 bits, 2 bits. All these are done using synchronous counter. All these are done using synchronous counter. So that's the thing. In synchronous counter, what do? We generate the states and then we design the counter. But using asynchronous, what is the scene? Using asynchronous, the scene is, let's just say you need to generate this pulse using asynchronous. So what you will see, there are 4 bits in the sequence. So if there are 4 bits in the sequence, if I take any up counter or down counter, so with respect to each combination, I will assign a particular bit. So if there are 4 bits in the sequence, that means I need to take 4 combination. So for 4 combination, what I will be requiring? 2 flip-flop. In this case, I require 5 combination. For 5 combination, I will be requiring 3 flip-flops. There you go. Okay, so that's how you will be solving it, right? So that's it. Very easy questions are asked in the GATE examination. Even in the interview, they will not focus much on this. They can just ask a simple question and generate this particular sequence. They will not even ask whether using synchronous counter or asynchronous counter. They will just ask, you need to generate this particular sequence. Will you be able to generate it? Yes, certainly you will be able to generate it. And if I had been the student, I will be using asynchronous counter because that is a much easier design. The only thing is here you will have to design the clear input. So if I need to design a clear input, so that also I can do quickly because I have the trick. So I will start right from the 0, and by using the trick, I will design this clear input as well, and F is already visual. Okay, so better I will be designing with this method rather than going for synchronous counter. Okay, synchronous counter also I can take, but that may take some time. But here also in synchronous counter, the problem of lockout can also occur. So better I will be designing in this method. Okay, so that's it about our what do we say, sequence generation. So I hope you must have visited our sequence generation. You must have understood how to generate a sequence using synchronous counter, using asynchronous counter by both. Okay, let's start this problem. In this problem, what they are saying, a traffic signal cycles from green to yellow, yellow to red, and red to green. Okay, in each cycle, green is there for 70 seconds, yellow is there for 5 seconds, and red is there for 75 seconds. So you are going from green to yellow, yellow to red, and then red to green. This is how you are going. But this is there for 70 seconds, this is there for 5 seconds, and this is there for 75 seconds. Okay, now what they are saying, a very important line will come. The traffic light has to be implemented using a finite state machine. The only input to the FSM is a clock of 5 second period. Okay, there is only one input, that is a clock, which is of 5 second period. What do you understand by that? In a FSM, there is always an external input and a clock, right? But here what do we see? Here we see that there is only one input, which is clock only. So based on clock only, you need to analyze this cycle. You need to make this cycle based on clock only. And clock has a frequency of, or you can say time period of 5 seconds. It has a time period of 5 seconds. So I will just make it. So this is a particular circuit I am having, and it is having a clock which has a time period of 5 seconds. So this is your FSM, this is what they are calling. But there is no input, no external input. Now what do you think what will happen here? So I will assume clock as a button. So I am pressing a button. That means initially green light should turn on. That button will be there for 5 seconds. I will again have to press the button. Then again green light should turn on. Because green light should be there for 70 seconds. Say yes or no? In first clock cycle, there should be green light. Then again there should be green light. Then again there should be green light. In that manner green light should go. After some cycles, when 70 seconds have been completed, after that yellow light should turn on. Yellow light is turning for only one clock cycle. Then yellow light will turn on. Then again if I am pressing the button, again one more clock pulse is coming. Then red light should turn on. Now this red light will turn on for 75 seconds. That means a lot of clock pulses will come. Clock pulse, clock pulse, clock pulse, clock pulse. So in that manner it will go. So now your question becomes is that you need to make a circuit which generates this sequence, that you go from green to green, green to green, green to green, green to green, then yellow to red, red to red, red to red, red to red, and then again back to green. So this is the question. Did you understand this point or not? You have only clock input. With every clock pulse, your output will change. Clock pulse will come, output will change. Clock pulse will come, output will change. But for the first clock pulse, you want green output. Then another clock pulse, you want again green output. Another clock pulse, you want another green output. We saw the questions, no? That you need to generate 0, 1, 0, 2, 0, 3 in that manner. That first clock pulse, you should generate 0, then 1, then 0. Or we saw these examples. That in first clock pulse you need to generate 0, then another clock pulse you need to generate 0 only, another clock pulse you need to generate 0 only, another clock pulse you need to generate 1. So in that manner you need to go, right? We have seen these examples. So now what is our task? Our task is just to design this. So what is the sequence required? Green, 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 then yellow, red, 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 then red. Now why I have written 14 times here? Because green is there for 70 seconds. Green is there for 70 seconds, and yellow is there for 5 seconds, and this is there for 75 seconds. Now in one clock pulse will come, that is of 5 seconds. One clock pulse is of 5 seconds. One clock pulse is of 5 seconds. So that will be there for 5 seconds. Then another 5 seconds, another clock pulse will come. So till 14 clock pulse, 70 by 5, till 14 clock pulses, 5 by 5. Till 1 clock pulses it should be yellow, and till 15 clock pulses it should be red. Are you getting this point? First clock pulse comes, green. Second clock pulse, green. Third clock pulse, green. Till 14 clock pulse it should be green. So 14 into 5, 70. Then 1 clock pulse will come, yellow. Then another clock pulse comes, red, 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 till 15. And then you again need to come back here. So this I forgot to make here, that I again need to come back to green. So this is the cycle: green, 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 yellow, red, 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 and then in that manner. Okay. Now your question is, you need to generate this sequence. We have two methods, using synchronous counter, using asynchronous counter. So let's design it using asynchronous counter. So what I am going to design? I am going to design it using asynchronous counter. So how will I design? Let's not see the solution first. How will I design? Using asynchronous counter. In asynchronous counter, what do we do? Do you remember? Do you remember this sequence? 0, 0, 0, 0, 1. Do you remember this sequence? How did we generate it using synchronous counter? What did we do? That 0, 0, 0, 1 we wrote. Then we got to know that these 3 0 are different. All these 3 0 are different. We need to differentiate them. And to differentiate these three zeros, what I need to do? 0 0 0 1 1 0, and this is already differentiated, so I can put 0 0. So how many flops you required? 3 flip-flops, right? Now what is the scene here? Green, yellow, red. Three guys are there. Okay, all three are different. Green, yellow, red. All three guys are different. So what I can do? I will call green as 0 0 0, green as 0 0, yellow as 0 1. This is my yellow. This is my green, and red as 1 0, and this is my red. Because three guys are there, to represent three guys I need 0 0 0 1 and 1 0. Say yes or no? Correct? Okay. Now the scene is, first I need green, then another green I need, then another green I need. In that manner 14 times I need green, 14 times. Then I need yellow one time only, and then I need yellow is 0 1, and then I need red. How many times? 15 times. Say yes or no? Till this everything is clear. Green, yellow, red, all three are different. I am representing 0 0 0 1 and 1 0. 14 times I need 0 0 0 0, then one time I need 0 1, and again 15 times I need 1 0 1 0 1 0. Say yes or no? Understood? Everything is crystal clear. Now till this point everything is clear, so now we can go to the next page. So this is everything I have written. Green is 0 0, yellow is 0 1, red is 1 0. So 14 times 0 0, 1 times yellow, and this is red. So this was green, yellow, red. Now what I am gonna do? These all 14s are different. No, with every clock pulse these cycles should come. With every clock pulse I am gonna design a synchronous counter. So I will give one clock pulse, then something will come. I will give another clock pulse, then another combination will come. Let's just say in first clock pulse this combination is coming, then in the next clock pulse this combination may come. Any another different combination can come. Basically all these are different, all these 0 0 are different. Now I need to differentiate it. If I need to differentiate these 0 0, how many bits I require? Tell me. There are 14 combination, 14 0 0 are there, 14 0 0 are there, and I need to differentiate all of them. So how many bits I would require? To differentiate two zeros I would require only one bit, 1 and 0, both are different now. To differentiate 3 0 I would require 2 bits, 0 0 0 1 1 0, all are different now. To differentiate 5 zeros I would require 3 bits, because from 2 bits I would do only this thing. Now I will have to give 0 0 to this. Now these two are becoming same, so that I don't want, so I would require 3 bits here. So I would take 3 bits, 0 1 1 1 0 0. If it is there for 14 times, using 4 bits what I can do? Using 4 bits I can generate 16 combination. Using 4 bits I can generate 16 combination. 0 0 0 0, 0 0 0 1, both are differentiated. 0 0 1 0, this is also differentiated. Then 0 0 1 1. In that manner I will keep on going, and any combination I can pick. Just I am not going to repeat the combination. Okay, I am not going to repeat the combination. That's it. So here I am gonna pick from 0 0 I am starting, and this is 14 times. So this would be my 12 or 13. From 0 0 I am starting, then 0 0 0 1 I can put, then 0 0 1 0 I can put, then 0 0 1 1 I can put, then 0 0 0 0 1 0 0 I can put. So these combination I have. After that I am gonna put 0 0 1 1, then I am gonna put 0 1 0 0, right? So I have differentiated all these 5 bits. Say yes or no? So 5 bits I have differentiated. If I need to differentiate the 14th bit, then I would require 13 here. That is of no use actually. That is of no use. You just understood that here 13 means 1 1 0 1. Okay, and this would be 12. So what did you understand here? You just understood one point, that is to differentiate these two bits, these 0 0 0, I require another 4 bits, and for this I would require only Any combination would work because this is already differentiated. Now all these are same. Again all these are same. And to differentiate them, how many combination I would require? Since this is occurring 15 times. This is occurring 15 times. And using 4 bits I can generate 16 combination. So yeah, using 4 bits I can differentiate them. Using 4 bits I can differentiate them. So anything could come here, and basically this could be our 14. Right, any combination I can define. Basically I have different 16 combination. I have 16 different combination. Using those 16 different combination I can differentiate them. So now what I am gonna do, I am gonna design this counter. That will be a tough task, but I am gonna design this counter. Then I will pick only these 2 bits, outward, these 2 bits out. So this is what I am gonna do. I design this counter. Okay, it will have 6 bits. So how many flops are required here? 6 flip-flops. 6 flip-flops. So I will design this counter, synchronous counter made using 6 flip-flops. Here we are having 6-bit output. There will be a clock. Now for the first cycle, clock is triggered, 0 0 0 0 will come. So here you will have 0 0. If you are having 0 0 here, then this will be lit. And here I will connect a LED. And the color of LED will be green. So in the next cycle, what will come? 0 0 0 1 0 0. I have designed the counter in this manner only. 0 0 1 0 0. What I have designed is that this is my initial state. Some Q I am writing. Then my Q plus will be 0 0 0 1 0 0. In that manner I have designed it. So in the next cycle, what will come? 0 0 0 1, again 0 0 here. So again 0 0 is coming, then again this is lit. In the next cycle, these values will change, but these will be constant at 0 0 for 14 clock cycle. For 14 clock cycle, these will be constant at 0 0. So these two will be constant at 0 0 for 14 clock cycle. So till 14 clock cycle, always this green LED will be lit. Say yes or no. Are you getting this point or not? This is how I am going to design using synchronous counter. This is not the end of the solution. Okay. Here our answer is saying that it should be 6 flip-flop. Now after 14 cycle, what will happen? After 14 cycle, this will come 0 0 0 0 1. After 14 cycle, 0 0 0 0 1 will come. 0 0 0 0 1 will come. So which one will be lit? This is a 2:4 decoder. So what decoder will do? Now D1 will be lit. So D1 will be lit. So this LED I will keep as yellow. Okay, this LED I will keep as yellow. After that, what will happen? In the next cycle, what will come? In the next cycle, 0 0 0 1 0 will come. 0 0 0 1 0 will come. 0 0 0 1 0 will come. That means this LED will be lit. This LED will be lit. So I will keep this LED as red. This will be my red LED. Why this is my red LED? Because at 1 0, if this cycle is coming 0 0 1 0, red should be lit. So now in the next cycles, what will happen? These bits will change, but these bits will be constant at 1 0 only. So always this will be lit, red will be lit. So what will happen? At each clock cycle will come, clock cycle will keep on coming till 14 clock cycle, green is lit. So at the output, this will be my final output. This I will keep in a box. This I will keep in a box, and that will be my final output. Now someone will ask, sir, what about 1 1? What about 1 1? Sir, what about 1 1? I will not even design it. In my counter, I will design in a manner that this 1 1 condition never even occurs. So this bit will go needless. So this I will not show at the output. I will not show at the output. So this will go needless. There is no use of this. Okay, I will design my counter in a manner that just as I reach here, I go back to this state. Okay, in that manner I will design my counter. Just as I reach here, I go back to this state. So 1 1 is not even occurring. So that condition will not even occur. So in that manner I will go, and this is how it will be lit. Green, green, green for 14 times, then yellow for 5 seconds, and this red for 15 seconds. So how many flops I am using now? So the answer that is coming out to be is 6 flops. But is that the best design? Answer that is coming out to be 6 flop. Is that the best design? This is my question. Sir, as of now, we cannot comment if that is a best design. Sir, design it using asynchronous counter. Then we can tell, sir, whether it is a best design or not. So now I am going to design it using asynchronous counter. Okay. Going to design using asynchronous counter. So which sequence is required? This sequence is required. Green, 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 yellow, red, red, red. This you have already understood. So this sequence is required. So what we do in asynchronous counter? What do? We will design either up counter or down counter. We have solved all the examples using up counter only. So here I am going to design up counter only. So first I will design up counter. First I will design up counter. That has how many combination? How we used to solve using asynchronous counter? How we used to solve? Let's just say I need to generate this sequence. So what I would used to do, that I would design 2-bit up counter 0 0 0 1 1 0 1 1. Then I will design a combination circuit. So if my 0 0 is coming, my output should be 0. If my 0 1 is coming, output should be 0. If 1 0 is coming, output should be 0. If 1 1 is coming, output should be 1. And then I go back to this stage. So again 0 0 is coming, output should be 0. 0 1 is coming, output should be 0. 1 0 is coming, output should be 0. And 1 1 is coming, output should be 1. So your counter will give you these outputs 0 0 0 1 1 0 and 1 1. And with respect to that, that particular combination circuit will give you 0 0 0 1 output. Say yes or no. You remember this example, right? Or shall I show it to you again? I hope you remember it, but again I am showing it. Where it was? Here it was. So we were designing, we need to generate 1 1 1 1 0. So first we designed the counter. First we designed the up counter. With respect to that, we were having 1 1 1 1 1 1 output and then 0 0. So what this counter would be doing? You will start from 0 0. You will start from 0 0 1. Then again 1. Then again it will throw 1 and then 0. So here I was collecting my final output. So I was getting 1 1 1 0 1 1 1 0 1 1 1 0. Now tell me one thing. Where we were? Here we were. Okay. So this is what we were doing. Now I will design up counter again. How many combination I total need? Total combination, how many total combination I require? 30 combination, right? 30 combinations required. Why 30 combination? Basically for 0 0 0 0, let's just say for 0 0 0 0 0, I can give green. Then 0 0 0 0 1, I can again give green. 0 0 0 0 1 0, I can again give green. 0 0 0 0 1 1, I can again give green. So in that manner I will give green green green. Then for one time I will give yellow, and then for rest of the time I will give red. So I require at least 30 combination. Say yes or no. I require at least 30 combination. यार भाई अब इन मक्खी का क्या बोलें यार. वेलकम टू राजस्थान. एक तो एसी ऑफ करके पढ़ाना पड़ता है. तो आप लाइक जरूर करना इसको. यू डू लाइक इट. ओके. Usually my subscribers are English guys, so I have to speak in English. So do like this particular video. Yeah. So what I was saying. So I was saying that we need to generate 30 combination such that to each combination I can give my output. So I will design up counter such that I get at least 30 states. Not at least, such that I get exact 30 state. Exact 30 states. So my target is to design mode 30 up counter. I need to design mode 30 up counter. Okay. I need to design mode 30 up counter. How many flops are required? 5 flip flops are required. Okay. So for mode 30, if I need to design mode 30, that means I need to use clear input. Use clear input as well. Because a standard counter will count from 0 to 31. That would be mode 32 counter, right? If I am using 5 flip flops, I will generate mode 32 counter. I will generate mode 32 counter. But if I need mode 30 counter, that means I need to use clear input. So that also I need to use. So how we will use clear input, that also I will show. But this is how I will design my binary up counter. This is my up counter only. Q0, Q1, Q2, Q3, Q4, these will be my outputs. Now, what I will do? So these combination I will generate. I will give one clock pulse. If I give first clock pulse, what I will have? 0 0 0. Then I will give another clock pulse, what I will have? 0 0 0 1. Then I will give another clock pulse, what I will have? 0 0 1 0. Till 14 clock pulses. Till 14 clock pulses. What is this? These numbers are 14. From 0 to 13. That means 14 combination. So till 14 clock pulses, my green light should be lit. So I am designing a combination circuit such that if these are the inputs, then it should give me 1. And I will connect the LED which is green only. Okay. I am designing my combination circuit in a manner that if these are the inputs, green should be 1. And the LED will be green, the way we have connected here. Now after that, what I am doing? I am designing a combination circuit such that if this is the input, if this particular input is there, then it should throw yellow light. It should throw yellow light. Only one combination. Here it should throw green light. And for this, how many combinations are there? 0 to 13, 14, 15 to 29. Why 15 to 29? If you count from 15 to 29, there will be 15 combination. 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. So there are 15 combination. 15 combination. And with respect to each combination, I need to throw red light. So I am designing my combination circuit in a manner that that particular combination circuit will have minterms from 0 to 13. So 0, 1, 2 till 13. For yellow, it will have the minterm of 14. And for red, it will have the minterm of 15, 16 till 29. 30, 31, 32 you do not want. That means in your counter, just as you reach 29, your 30 should be cancelled. 30 should be cancelled. So what is my 30? 30 will be Q5, Q4, Q3, Q2, Q1 and Q0. How do we get 30? 1, 2, 4, 8, 16. 28 and 2, 30. Yeah. So I get 30 in this manner. So what will be my clear input? This trick I have told. This trick is applicable only at specific places. What all are those places? That also I have told. Right? If you are starting right from the 0, this trick is applicable now. So clear input will be Q4, Q3, Q2 and Q1. So I will design my counter in a manner that it counts up from what to what? It counts up from 0 to 29. At 30 it should be cleared. So here it should be cleared. Okay. So now it will be cleared. And clear bit is Q4, Q3, Q2 and Q1. Okay. So this should be cleared. So this is how we usually show it, that this should be cleared. Q4, Q3, Q2, Q1. Okay. Now counter has been designed. These outputs I will have 0 0 0 0 0 0 0 1 0 0 0 1 0. These outputs I will have, and these outputs will be fed to a combination circuit which will generate me these outputs. So basically this will be the final design. This is my binary up counter using 5 flip-flop. This is the clear input. These outputs will be generated. Now these will be fed here. These outputs will be fed in this manner. Here and here, then they will be fed here as well. All will be fed here as well. Or then they will be fed here as well. In that manner, all will be fed. Then we are having combination circuit. What they are doing? So if these bits are fed to it, then they generate output 1. Which minterms are fed? Should be fed 0 to 13. If these minterms are fed, then they will generate output 1. And if they generate output 1, it will give a green light. So this light should be green. So what I am going to do is that this should also be clocked. So here I am telling this is my clock. Okay. This is my clock. So what I am going to do is that I am going to put this complete design in a box. Okay, this clock will be my one of the input. Clock will be input as well, but I cannot show it one page only. In one page it is very tough to show. So this clock will be my input. I will keep on giving the clock. Then I would know that this is my binary up counter. It will generate the output. Then these outputs will be fed to this combination circuit. This combination circuit, if these are the minterms, if here I am generating 0 0 0 0 0 0 0 0 1 till 13, green light will be lit. After that, at 14 minterm, at minterm 14, yellow light will be lit. And at for minterm 15 to 29, which light will be lit? Red light will be lit. Red light will be lit. So in that manner we will go. Okay, so this is my final design. And here how many flip-flops we are using? 5 flip-flops. So what they asked? Minimum number of flip-flops. The minimum number of flip-flops. So the answer would be 5. In the examination, I do not need to make this final design. In the examination, it will not take me 30 minutes to solve this problem. In the examination, what I will see? Okay, this question is based on sequence generation only. So this is the sequence I need to generate. So total 30 cycles I would require. How would I know that I would require 30 cycles? 75 seconds, 5 seconds and 70 seconds, 5 seconds and 75. 70 plus 5 plus 75. What that would be? 150. And 150, each cycle is of 5 seconds. So basically 30 seconds, 30 cycles I require. So 30 combination I need. With respect to each cycle, with respect to each combination, I can give 1 bit of output. So 30 combination I need. For making the 30 combination, I require 5 flip-flops. That would be the answer. That's it. And then I will get to know that if I design it using synchronous counter, then green, yellow and red, they have to be defined as per the bits as well. Then green should be given 0 0, yellow should be given 0 1 and red should be given 1 0. So if they are also defined as 2 bits, then to differentiate, then I will require 4 bits. So this is making me use 6 flip-flop. But if I am using asynchronous counter, then I get to know that if I am using asynchronous counter, then I get to know that this is my required sequence and I need 30 combination. And if I need 30 combination, what does that mean? That I require only 5 flip-flops. 30 combination means 5 flip-flops only. Okay. So if I require 5 flip-flops, I will generate 30 combination, and with respect to those 30 combination, I can generate my different outputs, which will be green, 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 then yellow, then red, red, red. So in the examination, within 30 seconds, if my concept is clear, I will write down my answer, that is 5 flip-flop. So it is possible to design it using 6 flip-flops as well. This is the design, but it is possible using 5 flip-flops as well. So these outputs are fed in this manner. These outputs are fed in this manner, and this is how you are generating it. Okay, so this is the complete answer. This is the complete analysis. I hope you enjoyed it. If you enjoyed it, consider sharing it with everyone, with your teachers as well. Everyone, like, it is always better to learn. Everyone can learn. So this I designed on my own. I thought that this is the way it should be designed. So this is the best possible solution as per me. If I get to see something else, if I get to learn something else, if someone is also posting something, if someone gets some good point, then also he can add the good points. So yeah, that's it from my side. I will look more into it. If I get a better design, then I will try to make a better design. But this question is framed by IITs, so certainly they must have thought of this design only. Okay then, yeah, thank you very much.